Go ahead.
Extra things to share. I don't.
Okay, go ahead. Good talking with George.
All
So
right.
you're going to eventually turn me on.
I think this microphone.
Purpose is it only for recording?
All right. So, hello everyone. As you're getting your drinks put together, I am delighted to introduce this week's ECE 590 seminar speaker. We have a distinguished outside speaker, Dr. Marty Schlecht of Syncor Corporation. Marty has a quite similar academic background as myself, bachelor's, master's, and PhD degrees out of MIT, and then he ended up joining the faculty at MIT, rose to the rank of full professor until he wisened up and decided there was a business opportunities to be had. So basically what he did, he started a company in 1998, Syncor Corporation, that designs some of the highest performance power converters out there, frankly. He has a wealth of experience, and he is here because he also heard that deep in the cornfields of Illinois are some of the most promising power electronics and power researchers. So he's here to both share his wisdom and potentially one day after you graduate, lure you away into a very successful industry career. So please join me in welcoming Dr. Marty Schlecht.
Thanks, guys. So now I know you grow corn here. I didn't know that before. I did too. So I've actually had an opportunity to talk with most of you already today, but I recognize there's some people I don't see. You guys are coming here next year, is that what I understand? Or some of you anyways, you are. So welcome. But I'm happy to be here. I guess I was told everybody with a name tag is somebody who's special coming next year. So thank you for coming to this talk. First, just let me give you the background again. Robert certainly did, but the things I want you to understand is I was what you are. You know, a graduate student in power electronics. Many of you, I'm sure, thinking about academic careers. I did that and so on. And for one reason or another, decided at one point in my life, almost 20 years ago now, to change that and go into business. And we could have a totally different conversation, but it would be about what I've learned since I've gotten out of school. There was a tremendous amount of things that I'm learning, and I'm happy about that. But generally speaking, it was 1998 that we got started at Syncor, and I'll give you a little bit more background on the company. We're about 350 people in the company, somewhat spread out over the world, but most of us in Massachusetts. We design, we manufacture, and we sell worldwide power electronic products. In the beginning, it was predominantly focused on DC to DC converters, but it's expanded way beyond that as the years have gone on. We sell them to various marketplaces, as you see listed there. In the beginning, it was the telecom, datacom marketplace, the Ciscos, the Nortels, Alcatel, and so on. But as time went on, we expanded out into the industrial marketplace, the transportation, railways, and so on, medical industry, and a heavy influence to stay into military aerospace as well. And to give you sort of the background, I really want to give you about why we're going to talk about quality and reliability is we do 100% of our manufacturing right there in that building on that wing to the right in Boxborough, Massachusetts, which is a small town west of Boston. We've never manufactured anywhere else. It's always been right there. And at this point, we've sold somewhere between 30 and 40 million different converters over the sort of 18 years, if you will, we've been selling it. So a lot of learning experience, a lot of feedback from all of that. Okay, so we're going to talk, and here's a picture of sort of what our products look like. Obviously, you could go on syncor.com if you want to see our website and get more information about it. But a lot of them are sort of these modules that I would call them DC to DC converter modules of one type or another, or a filter module, or something that's sort of like that, whether they be open framed converters or things built with a base plate for the military, encased, maybe more rugged for the high level of military. But also we build bigger system things. These are UPSs, similarly high technology, lithium polymer batteries. They're about half the weight, half the size of the competitive product that's out there. They're very rugged systems that you can put under a meter of water and they still work, and those kinds of things for the military. Inverters, power conditioners of sorts. So a lot of different bigger systems, not just the modules. Basically, these are made from those. Lots of times our customers buy these products and assemble them into their own special product, and other times there are things that are sort of standard like a UPS where we can assemble all that together and sell it as an assembled product. Okay, that's what Syncor does. Now, in terms of the context of talking about quality and reliability, I want to accomplish two things. One is to talk about what that means, just all to itself, but also to say, why do you do that? Ultimately, because my answer is because it's good for your business. It's good for Syncor. All right. When we think of the words quality and reliability, they come along a lot like motherhood and apple pie in terms of you should do this for goodness sake. Not true. And in fact, if you're ever involved in an endeavor to improve quality and reliability and people are talking about it because it's a good thing to do, run away as fast as you can. It's not about motherhood and apple pie. It's about saving money. It's about making money. And only if you have that attitude will you actually achieve quality and reliability. Otherwise, you're going to spend the next 2 or 3 years pretending you're doing something until somebody else figures out there's something else they'd rather do instead. And then your effort will wither away. If you will focus on saving your company money, of making your company profit, you will find yourself in a position of being the most powerful person in the company. If you're the driver and expert in quality and reliability, it is a powerful position, a powerful concept, but only if you treat it that way. Okay, that's my biggest summary. We could all stop there, but let's go down a little bit. And you're going to see me jump back and forth a little bit between the business issues and the reliability issues. When you sell a product to the world, you have choices. First of all, the question is, how do you get them to buy from you? How do you get the customer to buy from you versus your competitor? That's the problem. And how do you get them to do that at a price you'd like to sell it for so you can make a profit? Well, the traditional answer to that is first you bring a piece of technology that your competitors don't have, that your customers need. And they're willing to buy from you because that technology brings them something that's valuable to them, and they'll pay you for it. But you find, unfortunately, that no matter what technology you have, it doesn't take too long before your competitors match it. So there's a point in time where you just cannot continue to lead through simply technology. So what's next? What's next down on the list? And the answer is your ability to deliver products with flexibility. This means if your customer calls up and says, I need so-and-so number of units, 1,000 units yesterday, you can say, yes, sir, you should look on your dock. They're there. I don't know why you didn't look yesterday. That's deliverability. Flexibility is along the lines of, look, I know we ordered 1,000 of these for delivery 4 weeks from now, but today we want to change to 1,000 of those. Can you do that for me? Can you be light on your feet and make changes like that? Or are you going to lock me into something that I need to order that I no longer want? That's sort of the flexibility side of things, okay? Delivery is also, I promise you I'd deliver them on this date, and I did. I didn't deliver them a day early, which is important to people because they don't want to pay for them any earlier than they have to. And I didn't deliver it a day late. Well, that's important because they need to manufacture and they can't wait for your product to come in. So delivery is also on-time delivery. And what I want to say to you here is that your ability to do this well can cause you to be very successful in business. We'll look about it a little bit more. But your ability to do this depends on having a high level of quality and reliability in your system. If you don't, you can't have good delivery and flexibility. If you can't accomplish that, then your final place to reside is lowest price. You buy from me because I've got nothing to offer you but lowest price. And guess what? Lowest price doesn't make you any profit. In fact, it may cause you to lose money. So you don't really want to slide down the curve all the way to that point. You will not stay here forever. But in today's world, and it's been true for us for several decades, this is a great place to play where you can actually hang on to that for a long time because it's not in the realm of most people you're competing with. Okay? Now, this chart here, I want to convey a basic business concept to you that's not something I created or first described. This is a well-known concept. Your customer demands a certain product, And over time, this is what their demand looks like, the blue curve here. There's a ramp up time as they begin to use something new, some new piece of technology. And then there's an overall growth of their amount of need for that. Certainly way out in the future, it'll tail off. But right now it's growing. But also notice there's a variability on how much of it they need. It wiggles up and down. In the course of that customer deciding where to get that supply, it's going to look at what's called its low-cost provider. That's one of those companies that has nothing to offer but the lowest price. And one of the things that they've had to give up with, or several things they've had to give up with regard to being the lowest price, is they're not the first one there with the technology. They're not devoting the money to create the technology to begin with. And they're not really good at dealing with variability of manufacturing. They're good at just delivering you a constant rate. You told them 3 months ago what you want delivered today, and they can handle that. And it'd be better off if you told them 6 months ago. In other words, their lead times are very long. 3 months, 6 months. They're good at delivering a constant amount of outflow. Unless, of course, they drop the ball every so often. Something happens with the quality. They send out a bunch of products that don't work. Everything has to be put on ship hold. We have to figure out what this problem is and get it fixed. And all of a sudden, momentarily, they can't deliver any product or can't deliver as much product and so on. All right? That's the classic model of a low-cost provider. Now, there's a gap between what the customer wants and what this low-cost provider is delivering, and that's, of course, the shaded blue. That's where there's an opportunity for a company like Syncor. We capture the early business because we're the ones who created the technology. And as the technology becomes equaled by others, we fill in the variability of the demand because we have a flexible manufacturing operation when the competitor doesn't. And nicely enough, when the customer drops a ball, all of a sudden we get a lot more business than we thought we were ever going to get if we can be flexible and deliver when that occurs. We never can predict it. And generally speaking here, this is where all the profit is. This low-cost provider is providing with essentially no profit, just happy to have the revenue so they can employ people. All the profit can be made right through here, and that's our business model to fill in that gap. And as a general rule of thumb, you can say you're dealing with 20% of the volume is what we sell, but we accomplish 80% of the profit. And I think I go so far as to say people in this role capture 100% of the profit. The low-cost provider is essentially driven down to the point of no profit. Okay? Not a new concept, just something I want to share with you that's been well established and well understood in business. So the question is, how can you play in this role? Well, here is that technology leader kind of thing, so you get a good sense of that. From here on out, it's going to be about your manufacturing capability, your responsiveness, your ability to deliver, and that then relies on your quality system and your control systems and so on. All right, now let's go away from business and go into sort of the quality question. Let's deal with some basics. When we talk, I use the word quality and reliability. I'm not sure what the official definition of those two words are. Reliability tends to be more along the lines of over time, how will it perform? And quality tends to be more like, well, you ship me some products and some of them don't work. That's not very good quality, you know. So, but what I'm trying to capture is both those ideas together, and that's why I use the word. Maybe I'll stop using it from now. But generally speaking, it's important for you to understand that when you're producing product and selling it, this is long after you've designed it, there are 3 stages at which failures occur. You manufacture the product and the product, not all of it works. It fails while you build it. It failed to perform. This does not mean, since we're in power electronics, we tend to think of things blowing up. But it could simply mean it works, but it doesn't meet all of its specifications. It's got too much output ripple. All right? So there's a failure in your factory. You then ship all the working units to your customer, things that pass specifications. And lo and behold, they put them into their systems and turn the switch on, and the product doesn't work there. It supposedly worked when you shipped it, but it doesn't work once they installed it. So there's a failure in their factory. And then there's finally, they shipped out into the world what was a working unit, and over time, it fails in the field. Okay, and those are the 3 categories I want to talk about. My use of these dollar signs here is to say a failure here costs the least amount to deal with. It's in your factory. You figure out what the problem was. You had a resistor that was bad or something didn't get built right. You correct it. It doesn't cost too much money. You ship the product out, right? It works now, so you ship it out. When the customer has a failure in their factory, it's going to cost more. And one of the things they do is they return the product to you saying, this thing failed. And first of all, they've got to take it out of their board, then they've got to stick another one in, send it back to you. You've got to do an analysis. If there's something that's wrong, you've got to maybe send it down to your vendor saying, what's wrong with this MOSFET? The customer wants a complete paperwork of trailing of what all this is about. And so that's going to cost more money. But finally, if it's a failure in the field where your customer sent it out to their customer and it fails there, then it's a very expensive situation. We'll talk about it a little bit more, where you've got everything from a bigger problem that has to pass through several organizations back to you with multiple people thinking about it and so on. And second of all, the feedback on there's a problem, what do I do to get it fixed so I won't have any more such problems? Here you have an immediate feedback. We're using surface mount manufacturing. The screen that we have for putting solder paste down has a little bit of gunk in one of the pad openings. Solder's not getting put down on that pad. The part is not getting soldered down correctly. It tombstones up with the surface tension. As quickly as it takes to go through the manufacturing line, you see the problem, you stop, you go back and correct the gunk in the screen, you fix all the ones that got manufactured improperly, but you're up and going again. The feedback is quick. There's a problem when you send it to your customer and the feedback, and now could be months before you get it back. And it might have been quicker, but the customer doesn't use everything right away, or they use it right away, but they throw things that are bad into a bin and don't tell you about it for 6 months. And you say, well, why don't you tell me earlier so I could have closed that loop and fixed the problem, and so on. And then finally, when it goes out in the field, we might be talking about, look, this is a 10-year life here, and I care about failures all the way through that life, and stuff didn't show up for a long time, so longer feedback there. Now, what I want to say here, and it's a very important point, the higher the rate of failure you have in your factory begets a higher rate of failure when the customer gets it into their factory, begets a higher rate of failure when it's in the field. You must think of it that way. In other words, you cannot tolerate high failure in your factory. You say, but don't worry, I won't ship any of those bad units. No. If you had a bunch of failures in your factory, what that likely means is there's a bunch of things you think work that are on the edge of working. And they're going to fail at your customer. And there's a large number of failures there that, guess what? The ones that they nevertheless shipped out, they also are on the verge of failing, and so there'll be a large failure. So this is the critical feedback, which is good, it's cheap, and it's quick, that tells you a lot about what's going to happen out there. You can't, and we'll talk about this, you can't simply what we call screen out your bad units. Don't ship the bad units, just ship the good units and be happy. That's not the kind of quality control that I'm talking about here. All right, you may have seen this, but this is a classic graph to show you when you talk about quality and reliability. It's referred to as the bathtub curve for obvious reasons. And what this is over time, the rate at which units fail. What % of the population that you have in the field fails per unit time, per year, per day, whatever you want to talk about. The failure rate is what I wanted to indicate. And the thing that you should observe here is that there's 3 different regimes. And let's deal with it. The one on the left is called the infant mortality. And you can see the failure rate starts high and falls off. And then at the back end of time, and this may be 10 or 15 years out, you have a wear out period of time where the failure rate starts to rise up again. And in between, you have something that's referred to as the constant failure rate period of time. And what I want to do is talk about each of these 3 segments of this bathtub curve in order. But let's start at the back end, the wear out mechanisms. What is it that wears out? If we had a car, we understand it. The brakes wear out as you consume the brake pad. The bearings and so on wear out as the friction wears down the mechanics. But what fails in a power circuit? It's not like we run out of electrons. So what are the kinds of failure mechanisms that occur? And there's several different things we could talk about, but let's give some idea. Things corrode. Now, you would tend to say on a PC board with big wide traces, I'm not sure the corrosion is really going to mount up to much. But if I got an IC with a 1 mil thick wire bond coming down, that can corrode. Of course, we use gold or aluminum to try to stop that. But the point is things that are small might corrode away. The hotter something is, the faster that corrosion will take place. The more humid the environment is, the faster that'll take place. So exactly how fast corrosion will eventually wear things out depends on the environment, and that's an important thing to know, because now what I can do is do testing early on where I accelerate these problems. I put it into a hot environment, I put it into a humid environment, I maybe, well, we'll talk about the next mechanism, but I'm trying to put it in the worst case environment to see whether anything can fail more quickly so I can notice the problem. So corrosion is one of them. A big thing in power circuits, and by the way, you can apply this to your stereo equipment if you'd like, is thermal fatigue. What do I mean? Every time I turn the thing on, everything gets hot, everything expands, but things expand at different rates. And so there's a mechanical stress between them now. Typically, by the way, this is the purpose of solder. I forget the technical word for it, but solder is like silly putty. If you stretch it slowly, it stretches. If you pull it quickly, it will break. And solder has that parameter. Solder is the thing that says your PC board expands at one rate and your semiconductor device, metal and so on, expands at a different rate, and it's the solder that makes up the difference and is the thing that stretches. And so one of the things about this idea that if you move it too fast, it might break, one of the ways we accelerate this problem or see whether we have a problem is we go through thermal shocks. Minus 40 degrees to 100 degrees. We shift it from one chamber to the other chamber within seconds, and now the whole thing heats up as fast as the thermal mass will allow it to heat up. What we're trying to do is not say it was, it's going to be used that way. We're trying to say are our solder joints good enough to not break under that extreme fast change of expansion of them, or are they good? And if they're good for that, then they're really good for the lower thing. So that's a different kind of mechanism. And by the way, thermal mechanisms, the thermal mechanical fatigue here, it builds on itself. If I start to take a die that's soldered down to its metal header of a power MOSFET or something, and expand and contract. The stress is around the corners. Those of you who are mechanical engineering, you understand that. And so the corners start breaking free, and there's no longer a good solder joint between the die and the header anymore around the corners, which means they're not very useful for removing the heat around the corners. And then things start breaking further and further inward, and now because there's less and less of a thermal contact, there's more and more of a temperature rise, and therefore more fatigue as you go on, all right? That's the kind of thing. So you should turn on your stereo and leave it on. Don't ever turn it off. It'll last forever. It's not about running out of electrons. It's about all those thermal cycles when you're turning it on and off. Well, do you believe that or not? Depends what kind of amplifier it is. If it's a Class A amplifier and it's always hot anyways, if it was a different kind of amplifier where it gets hotter based on loud music versus no music, well, then you might as well turn it off. The telecom industry, be a little more serious about that. The telecom industry turns on power supplies and leaves them on 24/7. The military doesn't. It sits there and then the jet takes off and everything gets turned on and it comes down and it cools off again. So a different kind of environment. Vibration contributes to all of this, shaking things apart, wire bonds at the joints and so on. So these are kind of the wear-out mechanisms. And then there's things that are component-specific. Electrolytic capacitors or the electrolyte will eventually evaporate, depending on the temperature and so on. Optoisolators, little things that you may or may not know. In an optoisolator, obviously, you have a diode to emit light and a transistor to receive it, but you have a medium in between them. And as the light goes through that, as the photons go through it, eventually it clouds up that medium, and you start losing the gain. You no longer have the current transfer ratio that you thought you had before. And eventually, if you've designed for that, so you say, look, I know it's got a gain of X, but I can work with an X gain of 1/10 that much, well, then you're set. But if you need the gain of 10, otherwise you don't work, well, then you've got a wear-out mechanism that'll come into play. Okay, and you could say other things about other components. All right, so that's what I want to say about wear-out. Yeah.
So you haven't mentioned semiconductor failure. Are we at a point that we can trust like a carrier effect, electron migration, these things don't happen anymore, or?
Well, in your design ICs, right? That's what we talked about. Yeah. So in the world of power electronics and power devices, we don't have such small geometries where we worry about it quite as much as you do, where you're trying to get the latest piece of technology where everything is so small. Your current densities are higher than ours are in power devices as I understand it. So I wouldn't say no to you on that regard. I just don't think that's an issue on our power devices. Where I worry about our power devices is thermal cycling and all the connections we talked about. I also worry about the breakdown voltage capability of is something getting moist inside there? Is it getting corroded? Will I get breakdown around the edges? Those are the things I worry about. Not so much the things you talk about. Good question. All right, now let's go to the other end, and that's the infant mortality edge. What I want to convey to here, whether it's well done or not, is that what's happening now is we're weeding out weak things. We built it and we turned it on and some of them didn't work right away. And others are on the verge of not working. And others are a little bit further away from the verge of not working. And so there's this layering of weaknesses that you go on. And so the reason why this failure rate is getting better is you're simply weeding out the weakest things, and then you're exposing the less weak things, and you're sort of weeding them out. And it's really a continuous problem. It's almost, it's not a proper statement that the weakness fell out, but you eventually drop down to some constant level of, look, there's this weakness, and it's going to keep at this rate for a long time. Okay, so there's this layering of problems. And that's what I want to convey about that aspect of it for right now. Well, this slide will go on. What do you do about infant mortality? The last thing you want to do is send to your customer products that are about ready to fail. Not so bad if they fail within their factory, but what if they send them out to their customer and it fails there right away within a week? That's much more expensive. So you don't want to have this happen. And so generally, the approach here among a certain type of company and maybe also a certain type of American companies is to screen out the infant mortality. I recognize this will occur. What I'm going to do is before I ship this product, I'm going to put it into a burn-in rack. I'm elevating the temperature of it. Maybe I'll add humidity, and I'm going to let it sit there for some amount of time to get these initial failures, the infant mortality, done and gone before I ship the product. Okay? And that might mean a burn-in rack, that you burn in things for 48 hours, just making these numbers up. 48 hours until you begin to notice really all the failures occur within the first 24 hours, and then you can reduce your burn-in time to 24, and you begin to notice that most of the failures over time begin to occur only in the 12. And so you're working to get that burn-in time down by observing when do the failures occur, exactly how long does it take to weed it all out, and you observe it over time. Of course, very costly to do this in both delay and the expense of doing all this, but it's, as I'll show you in the next slide, it's not a great thing to be doing. Thermal shocking, we mentioned, is another way to screen out things that are about ready to break. By the way, we're doing all this screening. We're going to measure its electrical performance before and after. We're not just simply saying to this thing, is it a go or a no-go? Is it been shifting in its performance? And if I see a shift that's out of the normal, then I'm saying, hey, that's something I want to screen out. It may still work, but it's shifting too much. So I want to screen it out. Compare that screening with the issue of simply fixing the problem. Why are these things weak in the first place? Am I buying poor components, being delivered poor components from a vendor? Fix that problem. Fix the vendor, change the vendor, maybe screen it, maybe do whatever you have to do to screen out those components, but fix the problem. Maybe it's a design issue. Look, I've got a specification for the output voltage being plus or minus 5%, and my design is such that it can't quite meet that, and I'm too often failing it. Well, design it differently or open up the spec so that you meet it more often, one or the other. Can't open up the spec if the competition does better than you or the customer demands something tighter, so you better fix it instead. But opening up the spec is one choice. So constantly looking, and this I used this word with some of you before, the concept here is like a stream with rocks in it. You look at all the rocks that are sticking up, meaning you prayed out the failures and you take the worst case offenders and you fix the problem. Lower the water, look at the next set of rocks that show up. This is an old analogy people use in this quality business. Fix those problems. Lower the water, find the next problems. And what you're doing is what's referred to as continual improvement. And the concept here is to reduce your infant mortality all the way down to the point where it doesn't exist anymore. There is no distinction of infant mortality anymore. In other words, don't screen it out, fix it. All right, and that's what I want to present to you is what the real answer is here in terms of what you're trying to do. We got to a point in Syncor where we were finding that half of the failures that we found during burn-in were caused by sticking the converters into the burn-in rack sockets and pulling them back out again. The mechanical stress of doing that was cracking capacitors and other things like that. That was half the reason. So we just at that point finally said, done. We're not screening anymore. We'll do batch screening occasionally just to make sure we haven't lost the formula. But generally speaking, we don't screen anymore. We ship. We solve the problems and we ship. Okay? And that's where you want to go. This is, if you will, the modern world of how to handle infant mortality. Now, big difference whether you're selling a couple of million units a year and you have a lot of units to learn something from, and you're shipping 10 systems a year, maybe because you're selling to the military, maybe they're big systems. You don't have enough numbers to really know when you're selling 10. So the screening has its role there, but that's sort of where screening came into play. It was a lot of the military that drove the quality questions, sort of after during World War II and so on. And the quality questions were about small numbers of things, and so you screened them out. And it was really, if we go back over time, well, before you guys were even born, it was the Japanese who came along and said, no, that's not the way you deal with this. You design it out, as they started creating all the automobile, the industry that they created. And good American companies have learned that and taken it on as well. Those who are still stuck in a screening mentality should not be, unless you're dealing with just small units and it's the only way to deal with it. Okay, any questions about that? Now we get to the middle of the bathtub curve, which is the constant failure rate. And what I want to say here is when the percent failing is constant, what that means is that the population that's out in the world and working has an exponential decay. You know, an equation you're all familiar with, e to the minus t over tau, where tau is what's called the mean time between failure. It's a phrase you should get to know. Mean time between failure. It's not really clear to me exactly what that means, mean time between failure, except when I draw this exponential curve and say that's what tau is. Now I know exactly what it means. Okay, and I think you do as well. So the working population decays away. Let's talk a little bit about this. There's several ways to talk about mean time between failure. One of them is to do a calculation. And you'll find in the military there's a mil standard 217. In the commercial world there's a standard called Telcordia that talk about how you calculate, if you will, predict what your mean time between failure is. Whether this calculation is worth anything or not is another question. And by the way, in the calculation, after you've calculated the reliability, there's no place to say whether you hit it with a sledgehammer or not. You know, in other words, there's all kinds of questions that are not being asked by that calculation. But you can say, here's my calculation, and so here's my predicted mean time between failure. You can demonstrate it in your own facility by doing highly accelerated life tests, which is what HALT stands for. In other words, let me put a bunch of units and operate them for a bunch of hours and see how long it takes to get a failure or two failures, and from that calculate what the mean time between failure is. All right. The problem here is, what if I have a mean time between failure that's, you know, hundreds of years or more? It's going to take an awful lot of units for an awful lot of time during which there have to be no failures before I can demonstrate something like 10 million hours or 100 million hours. I may take a year to accomplish that, and a great expense. So I want to accelerate the testing by raising the temperature. I may even raise the humidity, as I talked about before. But I can only prove so many hours this way because it just takes too long. The best way to address what my real mean time between failure is to let the products go out to their field use and then know how much they're used, under what temperature conditions and so on they're used, and how many of them are failing. All right? That's where you're going to get your most data of all the converters you're producing, of all the hours that they're being run, and you're going to get the greatest data. The question is, can you get that data? And in our case, we're selling it to the telecom industry. This is in our early years. Syncor still do sell a lot to the telecom industry. There are several companies out there that are very good at returning every part that doesn't work to you. And so you have a good piece of feedback on what your failure rate is. You also know they're running 24/7. You pretty much know the thermal environment is. And so from this, you can get really good experience of what your actual mean time between failure is. But most importantly, again, on this continual improvement structure, you begin to see what is it that's the dominant failure rate. How do I fix it so it won't be there anymore? How do I fix the next one below that? And so on, this continual improvement. Typical numbers for mean time between failure and the kinds of things we make: 100,000 hours to 100 million hours, maybe even higher than 100 million hours. But just to give you an idea, if I did a calculation on our product, it might tell me it's a 2 million hour mean time between failure. Demonstrated in our factory, as far as we're willing to take it, maybe we can achieve a 20 million hour demonstration. out in the field, assuming we have all the data correct in terms of returns and so on. We think the number is 200 million. In other words, these.
How do you get those estimates? Or is it millions? Because that's a long time.
Yes, in fact, that's what we're going to talk about next. But the mill standard, by the way, the mill standard for calculating is a well thought out concept. It says use these rules for deciding what your reliability will be. Unless you know better, stick your own numbers in here. The mill standard is wide open. If you know better, stick your numbers in here. But when we take the reliability numbers that we get from our vendors for every one of our components, and we stick those real numbers into this calculator, we still end up with something like a 2 million hour calculation, when in fact, in reality, we achieve 10 to 100 times better than that. So I'm not sure what more to say about that. But your other question is, that sounds like a lot of hours, and I'm going to come back to that point. There's one point I want to make, go back to this bathtub curve. You get the sense, having talked about it now, you understand wear out, you understand infant mortality, and maybe this constant failure rate. It's all very exciting. What I want to say is almost everything mankind makes seems to have this kind of characteristic in terms of failure rate. This is not just something about power electronics or about electronics, everything. The most fascinating thing to me, and I want to convey this to you, it is also demonstrated by software. And think about that. Not a single piece of mechanics in it, and yet software displays the same bathtub curve. What's happening? Well, they ship it out to you and they thought it worked, but there's bugs in it. And people find the bugs, and they correct the bugs, and the revisions come out, and eventually you come down this infant mortality problem where there's not so many bugs left in anymore. And only occasionally do people do something that's never been done before, and they run into a bug, right, a failure rate. So the failure rate's low during the middle of this curve. Now, what's the wear-out mechanism? It's been so long that finally people have said, oh, here's a bug, here's a bug, here's a bug, and people start fixing it. But they didn't write the code in the first place, and every time they fix something, they make 2 more bugs. Or 4 more bugs that nobody knows about, and eventually it escalates, it avalanches on you, and the whole thing wears out, and the software's no good. So something as non-physical as software displays the same bathtub curve of failure rates. It's very interesting.
We have situations where you get toward the end of your hardware lifetime, so the software cannot catch up with it. We call that also a software failure.
Yeah, no, sure. And now, does that happen in our products? No, because we're not modifying the software. You know, the software is what it is. Maybe we've got a few revisions early on, but after that, we're done with it. Whereas a piece of Excel, for instance, would have constant needs to change its software as you go on and so on. But I can't actually tell you now that I've seen the wear-out mechanism of our products after 20 years. It's not like, first of all, we're not getting the feedback. Customers are not returning something to us after 20 years or after 10 years or so on. But second of all, I'm not having anybody say, yeah, your stuff it ran well for 10 years, but then it failed all over the place on me. We haven't run into that yet. So the electronics here are actually well designed, will last quite some time. All right, so that was about the bathtub curve. Now, let's go to the question, what am I doing talking about 1 million hours, 10 million hours, 100 million hours of mean time between failure? What does that mean? Well, 1 year has 8,760 hours if you don't count the quarter day that we really should put in there. And if you will, just let me round that off to 10,000 hours for a round number. So a year is 10,000 hours. Okay, you with me? So when I tell you there's a mean time between failure of 1 million hours, which is on the low end of the scale of what I've been talking about so far, that's 100 years. Or 100 million hours is 10,000 years. What am I talking about when I talk about a mean time between failure that's that big? It's just extreme. Why should I worry about it? Well, let's go back to the basic curve. If I have 1 million hours of mean time between failure, and I say that's roughly 100 years, then draw the straight line down. You know that the initial slope follows that straight line, right? Well, that means for very small distances like 1 year, 1% of the 100, I'm following that the curve follows that straight line. So that means I've lost 1% of the population. So 1 million hours mean time between failure, 100 years. Don't think about the 100 years. Think about it, you lost 1% of your population in the first year. Essentially 1% of your population in the second year, onward. That's the way to think about it. And now the question is, how painful is it to lose 1% of your population per year? Right? And obviously, as we change the numbers, those percentages will go smaller. Okay, so to put that into context, let's say a customer is buying a particular product from us. It's a quarter brick, does 100 watts. It's an assembly for us, about 250 components, and we sell it to the customer for $30. All right? And of course, the competitor is out there saying, no, 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 mine's 27. And the question is, should the customer buy us or should they buy the cheaper one at 27? Now, what I'll do, and I have done over the course of several years, is go to people and say, let me ask you a question. When you have a failure in the field, what does it cost your company when one of our power supplies or one of our competitor power supplies fails in the field? What is that cost of that? And I give them some numbers, half order magnitudes here. Now, they'll generally answer that question as $3,000 in the telecom industry, but most of them will say, I bet it's a lot more than that when you really factor in customer attitudes towards them in terms of failures and so on. What does it really cost to process all of that? It's easily $3,000. All right? Then if I ask the question, how long is this product of yours going to be in the field where you care about the fact that there's a failure or it matters to you? And generally, and I give them a bunch of years to choose from, and generally they'll say, well, at least 10 years that this product will be out there, that I care about that. Okay? So with those answers, and I talk to people, if you want to choose different answers, go ahead and choose different answers, but that's the ones I heard you choose now. Let me do some calculations for you. If the mean time between failure is 1 million hours, 100 years, then we're saying 1% of the population fails per year. Therefore, over the life that you cared about, 10% of the population will fail. And for that 10%, it's going to cost you $3,000 each. So averaged out over the entire population, it costs you $300 to own this $30 part. This is referred to as total cost of ownership. There's many other aspects of cost of ownership, but this is a dominant one. Failure out in the field costs so much money that it translates into a tremendous cost. If you only have 1 million hours, which sounded like a big number, in truth, it costs you 10 times more to own it than it did to buy it in the first place. If you have 10 million hours, of course, the numbers drop down by 10. It only doubled the cost of what it cost. To owning it was equal to what it cost to buy it. And if you go to 100 million hours, well, now you've dropped down to $3. Okay? So this should be a tremendous thing for people to think about, especially when they buy a large number of components so that they can see the quality results. The numbers are big enough so they could find, look, I say to people, buy half from me and half from my competitor. I don't know what their quality is versus mine, but take 6 months and you'll know the difference. You've got all the data for both sides, and you can tell me, based on this analysis, it's very simple, whether I'm worth $3 more than the other guy, or you can tell me I'm not. But just do this. Okay? Does everybody get this? Everybody understand this? Okay. I'm going to tell you something. I talked to people in the telecom industry for over 2 years. I talked to engineers, Cisco, wherever. I talked to procurement people. I talked to middle-level managers. And all of them sat there and nodded just like you. They intellectually get it. And when they're all done, said, not my job. My job is to get the lowest initial price. I'm not in charge of total cost of ownership. Every single one of them did. So as much sense as that made, it had no effect whatsoever. Now, we talked partly about procurement guys with some of this group here. Even if they thought it was a good idea, they wouldn't admit it to you. So the question is, can you see it in their eyes, even though they're not admitting it to you? But no one would actually take action on this. And that's frustrating. I think the answer is this. The world has become, and I'll just use Cisco as my example, but Cisco in a sense has two operations. One is called create a product. And it has a certain cost of creating that product, and therefore it has a certain profit. The other side is sell warranty. Not just we warrant this product, but if it fails, we're there within 12 hours with a replacement, so your business is up and running again. So there's a lot more to it. All right? And everybody's trying to maximize the profit of their business. So these guys are over here saying, lower that initial cost, I look more profitable, and that's what matters to me. The fact that you have more cost over on the warranty side of business, that's somebody else's problem. That's a different side of the company. And there's nobody who's actually saying, wait a minute, let's spend $3 more for this converter and save $30 for its quality over here, this total cost of ownership. Nobody's saying that, because by the time these two parts of the company came together, you were at the CEO level or the CFO level, and that person's got too many things to think about instead of something as simple as this. All right. So I think when I say the world doesn't pay attention to this, it's because the world has found great business in terms of just selling warranties. You know, when you buy something from Cisco, the warranty that you're going to pay to have this immediate fix if something goes wrong can easily add up to how much you paid for the product within 3 years. Double the cost of it. It's amazing how much you pay for the warranty of stuff, but you sort of happily do it, because what else are you going to do? You can't insist they make it more reliable. You can't go to somebody else very easily. There's only so many players here. So I think that's the answer for why this total cost of ownership, as much as it makes sense, doesn't get much play. Okay?
So you're excluding this, the whole idea of reputation.
Well, yeah, I'm going to go to some of those issues next. Yes, you're right. Maybe we can jump into it. We've talked about 1 million hours, or 10 million hours, 100 million hours looking really good, and maybe I'm at 100 and my competitor's at 10, and I'm saving my customers $27. I wish they paid attention to that. But you're right, George. One thing I should say is, if you got 1% failing a year, you got a problem. Because that's what happens. Although people don't pay attention to this trade-off, if you start causing a big problem, $300 a unit on average because you got a 1% failure, people are going to notice that. And what comes out of that is that you can quickly get yourself blackballed. You'll never be a vendor for this company again. And that's, so in other words, there's this threshold by which you've created a disaster, and then people pay attention to it. Beyond that, they're not paying attention to it. And that's my frustration, is it makes a difference whether it's 10 million hours or 100. It makes a big difference in the cost. But those numbers are both above that threshold of disaster, and so then they don't pay attention to it. So yeah, it's a good point that I wanted to make. Okay, so what do you do if that's the way the world reacts to your drive towards quality and reliability? The answer is you turn inward, and I don't mean, the answer is it always was turn inward. Quality and reliability should be your purpose, your desire. It makes and allows you to be a better company. Now, in some sense, it's very simple. Every time a unit fails in the field, you've got to analyze what the problem was. If you're a growing company and next year you're going to sell 5 times as much as you sold this year, that means you got 5 times as many failures to be analyzing just on what went to the customer and didn't work in their factory. And then you've also got the problem that your units are in the field for 10 years. So this accumulation of millions of units, well, now you're starting to get to a big number that even a fraction of a percent failing is a big number. And you've got to hire a lot of people to do this failure analysis. It costs a lot of money, distracts from things you'd rather do. Okay, so that's one reason to do it. Remember, the whole thing is a chain of quality, and so the better your quality system is, the fewer failures you have in your factory, and that saves you money too. Less number of units that are failing that have to be analyzed and repaired within your factory. But also, you know, when we manufacture something, this goes back to the flexibility question, do I need to create 1,000, start launch, if you will, 1,100 units to deliver 1,000? Because I expect 100 of them to fail in my own factory? Do I have to overbuild every time I have to meet a delivery? Or do I have to overbuild by 10 instead of by 100, or 1 instead of 100? You know, that's the question. So improving my quality system allows me to build just what I need instead of ending up with 100 parts that are fixable, but now what do I do with them? They're stuck in inventory, they cost me money, they took up my cash, and I may be able to sell in the future, but I don't know. But I had to overbuild because I have a quality problem. Well, I could just take those quality and say, Mr. Customer, it's going to take me 2 weeks to fix these so I can ship them too. But then that defeats the deliverability question. You know, was I on time on my delivery? Could I be flexible and so on? So no, now I got to overbuild to be flexible, but now I've cost myself a lot of money with these extra parts that I may or may not sell. All right, you can imagine that. A lot more intricacy than that, but you can imagine the playoffs that come inside. And then besides that, there's other benefits. You know, this goes to the point you were just making, George, is the last thing you want is the disaster story that everybody at Cisco thinks about you and they just can't get out of their head. They're constantly repeating. But then everybody else throughout all the industry hears about it too, and your competitors hear about it and tell the story everywhere, whether it's true or not. And so, you know, there's the thing called in sales called FUD, fear, uncertainty, and doubt. Those are the things you want to convey to your customer about your competitor, right? During the course of business, I've seen a lot of it, including the fact that I was either dead or dying in terms of part of the fear stories. Second of all, again, to the reputation here, when you don't have those problems, when your quality level is high, people don't just think about it as your quality is better, they think of it as your technology is better. Right? They think of it, and properly so, that it's about you being better designers. Don't necessarily see the whole interplay with the manufacturing operation and the constant feedback. They just see you as being better. And that, of course, is good. Yeah. Yep. And the only thing I would say there is we make statements about the customer as though it were a single person. And in fact, the customer is many people. And so while you can have this person here have that perception and another person maybe doesn't have that perception or has an agenda and doesn't want to accept that perception, and so creates a different one. So remember always that with businesses, there's not a singular answer, and the question is the people in power of decision making who, or of an influence of decision, what are they thinking? So it's always more than one. And I'll go back to this. What you're really doing, let me talk about leanness. You may have heard about the leanness. How do I bring in material just in the nick of time so I'm not owning it for 3 months before I use it? Manufacture quickly within a couple of days so that I can ship within a week of the product. And that's all called leanness, as opposed to I've got a bunch of inventory and I overbuilt in 3 months ago, and now when somebody orders something I can deliver quickly because I just pull it off the shelf, that kind of thing. I want to instead be responsive and lean. Why do I want to be lean? Well, one of the answers is it saves money to not have all that material in the house. It saves cash, but eventually I would make use of that cash. Maybe not. Maybe you'll have to throw stuff away because customers don't buy it anymore. But here's the real important thing. You can't be lean if you have poor quality. If you have poor quality, you're constantly in need of trying to cover up your mistake. All of a sudden I lost the formula and nothing works anymore in the factory. I've got to have enough stuff in inventory so I can rebuild that 1,000 units. You can't be lean if your quality is poor. You can only be lean if your quality is good. And driving yourself to be lean, therefore, then drives you to higher quality and reliability. Right? That's the drive. Force yourself to be lean so that you will force yourself to solve the reliability problem. And one begets the other. It's a closed loop on each other. The better you get, the leaner you get. Customers send you a bad set of components. Are you going to figure that out? A reel of components that are bad. Are you going to figure that out in a day? Or are you going to take a month or 6 months to figure that out? If you're lean, you're going to figure that out right away. And then you're going to do something about it right away. If you're fat, you're not going to notice that till later. Right? So those are the kinds of things you want to look at. Now, what do you do to achieve quality and reliability? Well, we talked a lot about it. Fundamentally, it's looking at the problems and fixing them. But what I'm trying to indicate here now in this slide is that it's at the level of the components you choose and the quality of your vendor's manufacture of those themselves. So it's down the chain. It's how you design as an engineer the product itself. It's how you manufacture the product. It's then how the customer uses it. And let me tell you something. Here's what happens to us. We take our product, sell it to a customer, they put it in their load board, they turn it on, and they say, this board doesn't work. And then they put their oscilloscope on the 3.3 power rail, and they say, there's no 3.3 there. Power supply must be bad. And they rip it out. Stick in a new one. Measure it. Damn it, it still doesn't work. Rip it out. Stick in another one. Still doesn't work. Maybe there's a problem someplace else. Maybe this load board has a short on it. Maybe there's a component that has a short on it. Now, what do they do with those 2 units? They said, these don't work, and rip them out. They don't solder them back in on the next unit. They used them. They soldered them. Maybe they did something wrong that will hurt them even. Or just, we said they were bad, so they're bad. Ship them back to Syncor. And now, literally, this is what happens. 3/4 of all the units that get returned to us from our customer's factory actually have no problem. So how do you address that issue? Well, it's not enough to simply say, hey, it's not my problem. you're still spending all this money fixing it. So what you got to do is go work with the customer's contract manufacturer to get them to stop doing that stuff. All right? And by the way, it's not just the cost, but then they're passing up the line that you have these huge failure rates, bad reputation, and so on, when in fact you don't. It was something else that was the problem. So you got to teach them how to handle it. So it doesn't just stop at what goes out the door here. And of course, it's how your customers design. You know, are they giving the proper amount of margin in their designs and so on, or is it just barely working for what they want it to do? And of course, it's the end user's environment. All those things have to be brought into play. So in the end, I've said this many times, it is a closed loop process. It's something you as engineers should fully understand. You observe the results, you make changes on the worst case thing. This is the most important thing. Always work on the worst case problem, fix it. Don't waste your time with the lesser case problems. This is the rule. The first couple of the big rocks are the ones you pull out first. You'll get to the smaller ones later, but focus. Focus on figuring the problem out for the biggest one. Create procedures for measuring things, for collecting data, for showing what you do. Make these corrections and commit yourself to this overall concept of excellence. All right. Now, I'll use a little anecdote here I did earlier, but I want to say it again. People do not go to work to work. At least they wish they didn't have to work. People go to work to play. That's what they want to do. And you are, as engineers, are in a sense doing that. You want to when you go to work, you want to play. And it's going to turn out, guess what, that there's a lot of work that you got to do at work, but you do get to play a little bit, but there'll still be things that are work, so I'm not going to tell you you're going to avoid it completely. But what I will tell you, that if you only have work for people at work, what they will do is invent a game to make work more interesting. And the game often takes on the character of things called empire building, backstabbing, information control, petty theft, searching the web for something to buy or pornography or whatever while you're not looking. In other words, not good things for the company. All right? If instead you give them games to play that are good for the company, they're just as happy now. They're playing an interesting game that's useful to the company. And quality and reliability and continual improvement is an excellent game. Everybody loves it from all levels of the company. Everybody loves to be engaged in doing that and finding the next rock and pulling out and say, look what I just figured out. I've been making a mistake all this time and it's been causing this rock. If I just stopped doing what I'm doing, this problem would go away. Isn't that exciting? As opposed to, well, I'm not telling anybody I'm making mistakes, or I'm just bored and that's why I'm doing it purposely. You know, that's a totally different attitude. You get that? So at whatever level you are within a company, create excitement by people, and this is a great game. You don't need to continually improve quality forever and ever and ever. It gets to a point where its economic value is minuscule, rate of return. But its greater value is it keeps people focused on something that's good for the company as opposed to wasting their time on something that's bad for the company. Okay? Now, in terms of what we've accomplished over 15 or more years, just to give you some charts, these are our mean time between failures of units in the field from our telecom customers based on the concept that they work 24/7, starting 3 months after we ship the product, and all failures are returned to us. All right, so not clear all of that is true, and you'll see that over time we've made continual improvements to move our mean time between failure from 200 to million hours to a billion hours. Almost an unbelievably high number, I would say. In terms of this curve looking like it goes down, like we've lost the formula, you can't project a mean time between failure of any given number unless you've had enough units out there for enough hours with no failures to actually justify that number. So what's happening here is not that the product is less reliable, but simply it hasn't had enough unit hours of working to justify a prediction any higher than that. That number hopefully will go up, but there's always that sort of delay of when will I know what my latest stuff is doing. Now, I don't know that we actually achieve a billion hours of mean time between failure. Are we really getting all the feedback? My answer is we look at a couple special companies who we know we're getting all the feedback from, and I can tell you we're achieving numbers in the 300, at least to 400, somewhere in this range. If not that number, then somewhere here. All right? That's one statement in terms of, but I think it's really pretty good. But more importantly on that curve is how it's constantly getting better. We're constantly figuring out what's the next thing to fix, and so on. And so that's the point. And I may have said this to some of you before. If someone selling you a product comes in and you say, what's your mean time between failure? And they say, well, it's 100 million hours. don't believe them, because anybody can say anything, and if it's a salesperson, it's most likely lying to you anyways. The question you want to ask is, show me the curve that shows how that reliability has improved over the years, and explain to me the various steps, the various stones that you took out of the water that caused you to go from one level to the next. If somebody can do that, which we can at Syncor, we can show any customer that analysis, then you know you're being told the truth. Okay, that's a pretty sophisticated story to make up. But don't give somebody too long to tell you the story, right? Just in case they're quick at it. This is a measure of what we call our supplier provided quality level. In other words, the failure rate in the factory of our customer. How many units failed? And we're generally achieving things below 200 parts per million. And those are pretty good numbers. Our competitors, our competitors are typically in the range of, I got to end up here soon, typically in the range of 1,000 or 2,000 and so on. By the way, just as another little anecdote, close to finishing, you say, how in the world can you sell a product that doesn't work when you thought it did work? Well, things can be damaged in shipping, vibrations and so on. Things are damaged when inserting them into the customer's board. So let's just talk about the ones that are actually bad. So things can go wrong in that interim. But companies do sell things that don't work. Companies that are having fiscal problems and problems with their technology not working and so on have been known to ship out in the beginning returned units that don't work, put them back in a box and send them out to a different customer, or send them out to the same customer. Disk drives often went through this process. There was one company that started doing that, and after a while just started sending out boxes with bricks in them. Never intended for it to work. It's not even a hard disk. Just trying to ship stuff to meet shipment goals, to meet revenue goals, to keep the stock market up where it needs to be for yet another quarter so people can invest and get their stock sold. So all kinds of stuff happen like that. So don't be surprised when occasionally people are meeting their objectives for on-time delivery by selling you stuff that's bad. Oh, I didn't know, return that to us. Meanwhile, this figure of merit, we're pretty good at on-time delivery, aren't we? Well, what they're doing is shipping you known bad parts. Don't be surprised about that. All right, so as a final slide, let me say this. I want to convey this concept. You as budding engineers, think of things you want to design as this left triangle is. And I did too as a student and as a professor. How do I design something for the peak of performance, better than anybody else can do? I can write this stunning paper about the stunning efficiency and watts per cubic inch and transient capabilities and all this stuff that no one has achieved anywhere else in industry. But I only had to make one of them. And it only had to work long enough for me to take the scope pictures. And it only has to work at room temperature. And I know how to turn on all the buttons and so on to make it work without failing, right? I got a different problem. I got to design for robustness. People at Syncor do, not me. We've got to deal with a wide range of components that are available to us as they vary, plus or minus, not within their own rights in terms of their specifications, but over years of buying them. We've got to deal with the variability of our manufacturing operation over years. We've got to deal with our customers' variable use of the product in their designs and also in their temperature and voltage ranges and so on. We've got to deal with their manufacturing process and so on. And so you have to design a product that's robust. And that's what I'm trying to indicate with that flatness on the top of the pyramid. And the question now is, how do I achieve the world's best performance, not with just one unit, but with millions of units? How do I achieve performance with robustness? Now, maybe I can't do quite as well as somebody did here or there who didn't have to worry about robustness, but I got to do better than my competitors. That's what I got to do. And what I'm trying to convey here is this concept that actually in the world of designing for manufacturing, the engineering task becomes more complex. It's not simplified because it's something for manufacturing. You've got to deal with all the things you're presently thinking about. How do I maximize the performance of something electrically? And then add another 10 parameters, constraints. The issue becomes far more complex, far more multidimensional. And it's fun. It's a fun way to be an engineer and do these things. And so, at least when I went through school, it was a little bit, from my professors, a little bit of, well, the highest goal in life should be to become a professor, like the guys up in the front of this room. But if you have to go to industry, go to R&D. Certainly don't become go to a company that manufactures something. Well, in truth is, companies that manufacture something and address this issue and so on are the most fascinating places to work because the intellectual process is far more complicated. You really can shine as an engineer when you do this. All right? So that's what I'll stop because I know I've overrun my time, but we could talk for days on this topic. Thank you. Okay, you can go.
So knowledge advancing, you have to put up specifications. For example, in telecommunication, the technology might be useful for 5, 6 years, then you have to go out and change it. So in your philosophy of running your company, does it make sense to intentionally lower the quality, to maybe keep the prices the same, or lower the prices to match your lifetime of devices with the field lifetime of the technology?
Yeah, remember, I'm not really so concerned about, gee, will mine last 20, it's not a wear-out mechanism, right? My question is how many will fail the first year and every year after, right? Those are the things I'm concerned about. So whether a customer changes after 5 years or after 10 years is almost not relevant to me. What I care about is I'm not tolerant of a 1% failure per year, right? Regardless. But the other question is, at what point will we change a component? Will we say we're no longer going to buy the capacitors from this company, we're willing to buy the capacitors from that company because it's cheaper, or maybe they have something better? And will we risk, that analysis of total cost of ownership? Well, we got to speak the same story ourselves. Will we risk ending up a total higher cost of quality just because we tried to save a penny or 10 cents by buying a component from somebody else? And it's a very tricky question for which we spend a lot of time proving to ourselves we're not making a mistake. And that's not just an issue of trying to save money on a cheaper component like a capacitor from one vendor from another, but stepping up from buying MOSFETs from Siliconics to buying them from Infineon. At what point are we willing to believe the Infineon parts are acceptable alternatives from a quality point of view? And then it goes to, at what point are we willing to use silicon carbide diodes instead of silicon technology? What do we think about that quality versus what we're achieving as a result? And so what is surprising is you start a company based on leading edge technology and being a technology leader, and very quickly you begin to understand that actually it's dangerous to change too much because you know what works, but you've got to change, and so you have to change in a controlled manner. The issue is always feedback. It's never, I made a mistake when I changed. No, if I made a change and it causes a problem, my mistake is if I don't pay attention to it. All right, that's the mistake. So be willing to change, but feedback. And that's what. So a little bit of scattering on what the question was, but go ahead.
So if you go back to the slides here, I'm curious, as you go from 4 sigma, 4.2 sigma to closer to 5 sigma,
Yeah.
what's that block that you pulled out of the screen?
Yeah, well, yeah, it was, you're going back over decades here. Ceramic capacitors, brittle things. You learn over time that you ought not put them, by the way, we build maybe 10 converters on a panel, and then we separate them out after they're built. In the beginning, I'll tell you quite frankly, we separated them they had little score lines on the panel, and we put them on a knife blade and we snapped them. Could you imagine that stress being placed on a ceramic capacitor located near the edge of the converter? All right. Now we don't do that anymore. A long time we changed it. We route the board out except for very small islands before we ever build the panel, and then we route the rest of it out so there's no snapping of the panel. All right. We don't put the capacitors near the edge of the board, near the corner where all the stress would be. We talked about the solder being the thing that takes up. So here's a pad for a capacitor with the terminals on each end, and you solder, like that, and the solder causes a fillet. You're trying to avoid sharp corners in the fillet so that there won't be any high points of stress. Well, that all looks good like there. I got the right amount of solder, so it has a nice shape. But let's look down from the top. If my pads look like this, then I got fillets all the way around, and there's a stress point at the corner. If instead I make my pad look like this, there's only a fillet along the long edge, but not near the corners. You get my point, and so I've avoided those stress points. So little bit by little bit, you learn these things. Either you learn them because you think of them yourself, or the capacitor company goes, no, you got to do this. They've already learned it, and they teach you. Little bit after little bit, you learn how to do things right. You learn how to put the spaces between traces right on boards. You get design rules that you follow because you've learned they're the good ones. You get rid of vendors.
Yeah, so as a follow-up question, what you said, so that makes the point of quality. So how often do you spend time teaching a customer as opposed to spending time finding those rocks? Is the rock sometimes the customer is doing that to you, or
Yeah,
like I'm curious your role, how much time you spend teaching versus in the lab solving your own problem?
Yeah, and so in the beginning, I spent a lot of time, as I said, with the total cost of ownership, helping people understand this importance of this thing. My overall result of that is nobody cared. So instead, I'm trying to explain why it was important for us and why I think, I should say, by the way, we started, as I said, 98, 99 when we released our product. In the early 2000s, 2002 or so, Cisco, John Chambers running the place, launched this quality endeavor inside of Cisco. Announced to the world, big committee, president was in charge of the whole thing. We're going to focus on quality. That's what our customers want. And they, among other things, chose a steering board of their vendors that had the highest quality to help them learn how to do this. And Syncor, being only 4 years old, power electronics, certainly not high up in the category of important things, right? We're just, as I say, a little bit higher than the sheet metal, a little bit below the fan in terms of relevance to people. We were asked, and I was asked to be on that steering committee of that quality company. And so I'm off on a little story. I heard them give up at their opening presentation about essentially saying this was motherhood and quality. And I stood up right in front of their meeting and said, no, you say that, 2 years from now, the whole company's going to be thinking about something else, and you're going to try to figure out how to wind down quietly so nobody knows you stopped doing anything. If instead you add, it's about saving money and improving this, you'll be the most important people in this company. They didn't listen to me. I don't even think people understood it. And within years, the whole quality endeavor was not something anybody needed to talk about anymore, and everybody was sort of quiet about the fact that it died away. All right, so you got to believe it. It's good for you, and yeah, it's good for everybody. It is. It's just start by believing it's good for you. That's where it really matters here. And just be good engineers all the way along the line.
We're a little bit over time. Why don't we, if you have more questions, maybe you can stay a few minutes for individual questions. And I also do have some places as well. So let's thank our speaker.
And I thank you. It's a great deal of fun.